Okay. Great. Hi everybody. I'm Andrew. I guess this is today I'm going to be presenting work with John Bostanci from Columbia and Vinod from IT. Um, this is an oracle separation between quantum and classical advice using good codes. Okay, so let's get started. So just as like a intro into the topic of what we're going to consider today. So in classical complexity, there are some like natural classes that we normally consider to represent the like set of algorithms that are efficient, whether that's with like non-uniformity or with non-determinism. And so we have these natural classes BPP, MA, and BPP poly, which capture set of classes of a set of classical algorithms that are efficient by themselves or with proofs or advice. So for us, we're going to try to consider what happens when we try to generalize to the quantum setting. So the natural analog of BPP is going to be BQP. But then that raises the question of what is the correct or what is an appropriate quantum analog for MA and BPP poly. Okay, so to consider what that means, we should revisit the definition of MA first. And so we're going to use this proof viewpoint of MA. So recall that a language is an MA if there is a polynomial time classical verifier and some polynomial bound on the proof size, such that if an instance is in the language, then there's a small polynomial sized classical proof that convinces the verifier with probability at least 2/3. On the other hand, if the instance X is not in the language, then no matter what proof is sent by the prover, the verifier will not accept with probably any more than 1/3. So in this picture, we have Merlin, who's kind of an inefficient and all-powerful prover, and he will generate some kind of classical proof and send it over to Arthur. Arthur is restricted to be a classical and an efficient verifier, and he will use the proof to decide whether X is in the language. So in the quantum setting, there's kind of two natural generalizations we can think of. So the first thing is we could ask if Arthur himself can be quantum, even if the proof is classical. And if this is the case, then we call this class QCMA. And we can also ask for even the proof itself to be quantum, in which case we have a class of QMA. Okay, so roughly speaking, the matrix sound looks like this. We can classify the complexity class based on whether or not the proof is classical or quantum, and whether or not the verifier is also classical or quantum. It doesn't really make sense to have a quantum proof and classical verifier. So that is the only class that is not here. But for all these other categories, we have MA, QCMA, and QMA. And relatedly, we can also talk about quantizing BPP poly based on whether or not the advice and the algorithm itself are classical or quantum. So if the advice is and the algorithm are both classical, then we have the usual class of BPP poly. If we make the algorithm quantum, we have BQP poly. And if we make the advice also quantum, we have BQPQ poly. So I guess like why should we care about these different classes? So as many people may know, the local Hamiltonian problem is a QMA complete problem, and this is sort of a quantum version of a CSP. It's related to a lot of different problems in physics. So as an example for us, like physically relevant Hamiltonians, many of them happen to be QMA complete. And so that means if that QMA is equal to QCMA, then these local Hamiltonians actually have simple low energy states. By simple, I mean like they have small small circuits that prepare these states. And that seems fairly unlikely. We have some evidence to show that at least we don't have like a very small depth circuits for all of these local Hamiltonians, but we don't have a ton of evidence, but we still think that these classes are not the same. And similarly, if BQPQ poly is equal to BQP poly, that would imply that any circuit that uses quantum advice, if the quantum advice is actually helping the circuit, that means we can always like dequantize it and simulate it using just classical. Okay, so what can we actually say about these classes? So unfortunately, these classes seem like they'll be very difficult to separate in the unrelativized world. That's because we know that QCMA contains P and QMA is in P space. So if we want to separate QMA from QCMA, then that would already imply separating P from P space. And similarly, BQP Q poly, separating BQP poly and BQP Q poly would also imply breakthrough circular rounds. So as of now, the next best thing that we can hope for is an oracle separation. So what is an oracle separation? That's in the oracle separation, the goal is to prove that different complexity classes are distinct when they're given access to some object, but only in a black box. So for quantum complexity classes, there are different kinds of oracles that we can consider. One kind of oracle is a quantum or unitary oracle. This is one where we have a family of unitaries that all the algorithms in question can apply. We also have classical oracles, which are kind of a special case of unitary oracles, and those are ones where we have a function, a Boolean function, that is evaluatable at any input of any length or in superposition. So this is a particular type of unitary. Okay, so as one note, in general, these classical oracle separations are by definition always quantum or unitary oracle separations, but it's not necessarily the case that when you have a unitary oracle separation, you can also get a classical oracle separation. And even the correct notion of access for a unitary oracle is a little bit unclear. So really the gold standard for an oracle separation is a classical oracle. So I guess like what is the history of what we know for these two problems? So for the setting of QMA and QCMA, this is a problem that's been studied for a very long time. It's first introduced in 2002 by Aaronson and Nirkhe, who asked, they defined QCMA and they asked if these two classes, QMA and QCMA, were distinct. And we started with a series of works, starting from Aaronson and Kuperberg, who gave unitary oracle separations, suggesting that these two classes were maybe not the same. They tried to get a little bit less unitary, a little bit closer to a classical oracle separation, but they are, for the most part, still very inherently quantum. And then recently, there were a few of these works that gave oracle separations for with classical oracles, but with various restricted models, whether or not that meant the witness in question or the proof was restricted in some way, or the verifier and the prover were restricted in how they accessed the oracle. And then last year, there were these two works from Liu, Matrita, and Yuan, and also from Zhandry that proved that you could get a full separation between QMA and QCMA, but only assuming some kind of pseudo-randomness conjecture, which they couldn't prove. And okay, on the BQP Q poly and BQP poly side, the question has been less studied. It was first defined in 2004 by Nishimura and Yamakawa. Aaronson and Kuperberg also gave unitary oracle separation in their original paper. And there was only one other work from Pelecanos and Yamakawa that gave a restricted separation for these two classes. Recently, as you guys may know, there was a classical oracle separation for QMA and QCMA by Bostanci et al. This was the first classical oracle separation for these two classes. However, there's some caveats with this work. So the first thing is that the work is a little bit complicated. It uses pretty heavy technical machinery, and it borrows a lot of tools from physics. It also seems pretty difficult to extend this particular proof to the device setting. We might get into that a little bit more later. Questions. The first is whether or not we can conceptually simplify this oracle separation between QMA and QCMA. And the second is whether or not there is a oracle separation for quantum and classical advice. So what are our results? We show first that there is a classical oracle that separates QMA from QCMA. This is basically already proven in the Bostanci et al. Paper, but we give a much simpler proof that will be based on what we call the code intersection problem. And the idea will be that we'll use mostly elementary techniques. Hopefully, they'll be simple enough that I can explain basically the entire proof. Okay, and the second is that we show that using this idea, we can pretty easily extend our oracle separation to one for a device as well. So this is the first classical oracle separation for quantum and classical advice. In fact, our separation is a little bit stronger than just showing that BQP poly is different from BQP poly, because we also place our problem in NP and co-NP. It's not clear, on the other hand, whether or not there is a natural variant of the problem used by Bostanci et al. That could be placed in NP. Okay, so let's get into the technical content. So as a starting point, we want to consider the problem of set size estimation. So imagine we want to estimate the size of some set S, promise that it's either at least some threshold L or it's below L over 2. So there's kind of a gap in our promise, and we want to determine which case we're in. Okay, so if we have access to the membership oracle for S, the question is, how hard is this problem of deciding which case we're in? So that kind of depends on what this threshold is. In the first regime, if our threshold is very small, so the sets in both of these promises are very potentially very small, then the good news here is that this set size estimation problem is not in QCMA. Unfortunately, it's not even in QMA. On the other hand, if the threshold is very large, so both the yes and no instances are promised to be very large, this problem is in QMA, but it's also very easy because it's even in BPP. That's because we could simply take a machine that samples a random point and checks to see if it's an S or not. Okay, so there are kind of two potential approaches if we want to use the set size estimation problem to give us an oracle separation between QMA and QCMA. So the first idea is maybe we can make the small regime a little bit easier for the verifier. And so to do that, what we would do is we would add some secondary oracle or some auxiliary information to help make the problem easier for our verifier. Essentially, the idea that a lot of previous works have taken, whether or not we consider the expander mixing or the spectral correlation problems, this is essentially the idea of the previous separations. The downside is that often what will happen is that the oracles you'll need are going to be dense or require many outputs, and those are difficult to reason about. Okay, so the approach that we'll take is to actually take the easy case and make it a little bit harder. And so we're using this idea from 𝖊𝖬𝖬𝖠, Pelecanos and Yamakawa of embedding our dense oracle, which is easy, into a much larger space. And we'll make it so that the indices that have the useful information about this oracle are going to be really difficult to locate. In particular, if we have some search relation R, we're going to define an oracle that will only give us information about whether or not X is in our set S if we can find an appropriate witness Y that is associated with X. So our new goal will be to distinguish a large set S from a small set S as before, but with this modified oracle. The picture is roughly as follows. So this O prime S is our original set of yes and no instances, and those are ones where the oracle is either entirely ones or mostly zeros. And as we see in the bottom, that's our new modified oracle. We kind of embed each of the bits of this original oracle into locations that are determined by the search relation. Okay, so I guess with that in mind, what kind of properties do we want from our search problem? So revisiting what I was saying earlier, I guess we want to embed our oracle, which is dense, into a much larger space using some search relation. So the question is, what properties do we want from our search problem? So of course we want the search problem to be relatively sparse so that it isn't easy. Too easy, but we want it to be doable if we have a quantum state or proof or advice state. And we want it to still remain hard if we have only classical advice or proofs. Okay, so candidate problem is going to be the code intersection problem. So I'll define that second. So if we have some code C, which has an alphabet sigma and is of length n, and we have random functions h1 through hn, the code intersection problem is to be given I guess a hash value x, which is in 0, 1 to the n, and to find a code word that hashes coordinate-wise to x. So we want each coordinate to kind of hash to x. So in this picture, we can have the purple dots as the code words. They're spaced. There is some high dimensional lattice, and each of these hash functions imposes some kind of restriction along each coordinate. right? So the work of Yamakawa and Zhandry show that this problem of code intersection is very easy if you are allowed quantum queries to the hash functions H1, but it's hard if you only have classical queries. So the problem here, of course, is that if we allow quantum queries to H, this places our problem in B2P, which is also contained in QCMA. So what we're going to do is try to look at the Yamakawa-Zhandry algorithm for this problem and see how to modify both the candidate problem and the algorithm. Okay. So here's like probably the only side that will require some quantum. We're going to take a look into how the Yamakawa-Zhandry algorithm works. So first, one observation is that it suffices to prepare the state that is the uniform superposition over all code words that are in the relation for any x. So our goal, remember, is to find a code word v that hashes to x. If we can prepare the state over all such v, then we can just measure the state and produce a valid v. And the observation that is made by Yamakawa and Zhandry, but ties all the way back to this reduction from Regev, is that psi here is the pointwise product of two states, one which is all of the pre-image states of each coordinate. So basically all of the xi's that hash, all of the vi's that hash to some xi, and also the set of all code words. So if we take the pointwise product of these two states, phi1 and phi2, we end up getting our desired state psi. The second state, phi2, doesn't have anything to do with H. It depends only on the code. Okay. So that means that by the convolution theorem, if we apply the Q of t to psi, that's equivalent to applying the Q of t to phi1 and phi2 when convolving them. And that means that if we can prepare the state on the right-hand side, this Q of t, the convolution of these Q of t's, we'll be able to, we can simply then apply the inverse quantum Fourier transform to the state and we'll recover psi. Our new goal is to do exactly that, to prepare the convolution of these two states. So what is the so how would we prepare these two states? So the first thing notice is the Q of t of phi2 is essentially the uniform superposition over the dual code word C, if C is a linear code. And there is some distribution D, some density function that dictates how much weight gets placed on different vectors in the Q of t of phi1. So roughly that will look like some sum over EV0, where E is some vector and sigma to the n, V is a code word in the dual, and the weighting depends on the Q of t of phi1. If we start with this state, which we can prepare just the tensor of these states, what you can first do is we can add the first two registers to the third register, and then we can subtract the first register from the second and third registers. And this will give us a state which looks very similar to the state that we want to prepare, except it has this V, extra V remaining. So if we could decode V given V plus E with high probability over a density function, then we would be done, because we could take our V plus E, figure out what V is subtracted, and then we would have our Q of t state that we want. Okay, so what is this density function? It turns out that Yamakawa and Zhandry show that essentially this density function is a random vector that has Hamming weight n over 2. And they also show that if we take C, yeah, so essentially our goal here is to gonna be able to try to decode this like noisy code word V plus E over some error distribution. And yeah, so we're going to show that if we take C to be an FRS code, a folded Reed-Solomon code, and it has a good enough rate, then we'll be able to decode the dual code with pretty good probability. Okay. So recall that our problem before was that this coded intersection problem is in BQP. And so our goal is to try to take it out of BQP. So this observation is due to Liu, is that there is some pre-processing that we can do for this algorithm. So first, the only time that the hash functions h1 through hn are ever used is to prepare all these like pre-image states for phi1. And the set of pre-image states for any x have a lot of overlap with each other. In particular, they're like any phi1 is composed of n of these like 2n different states, which consists of like for each index I in n and each like bit in 0, 1, the set of all like alphabet symbols that hash that bit. So if we had access to these 2n different states, then we could prepare 𝖊1 for any x. Okay, so the idea here will be to use the advice, as our advice state will be simply to use exactly the states that we need to prepare 𝖊1. Okay, so now we can give access to only this like larger oracle OS and not the hash functions as well. But now our problem is not no longer like obviously in PQP. And we can check that this problem still remains in QMA. The reason is because we can take our advice state, our preprocessed advice, and sample a random x, use that random x, and to construct the state 𝖊1 that we want. 𝖊2, remember, doesn't depend on the hash functions and only depends on the code word, so we can do that as well. And then we can run our algorithm, the second phase of the Yamakawa and Zhandry algorithm, and we'll be able to generate a code word that is in our relation. And so the question that remains is whether or not this set size estimation problem is still in QCMA if we only give access to this oracle O. Okay, so how do we rule out all the QCMA algorithms that we can get? So A will be very simple. So suppose there's some QCMA verifier V that makes poly n queries to this oracle. Let's consider the behavior of the verifier when it queries a yes instance versus a no instance. So in particular, let's consider when it queries the yes instance where S is like the entire set, and the no instance where S is like the empty set. Okay. So because the full set is a yes instance, that means that our verifier should accept, given some proof, that means there exists some proof pi sub h that causes our verifier to accept with probably at least 2/3. On the other hand, because the empty set is a no instance, that means that the verifier, given the same proof, will accept with probably at most 1/3. So in some sense, the proof pi is giving the verifier V some ability to distinguish these two oracles. And if V were a classical algorithm, then it's not too hard to see that a random query of a verifier to the no instance should also produce a point that differs between the yes and no instances with good probability that is proportional to the number of queries that you make. That's because if you made a bunch of queries to this empty set and each time you had a very low probability of putting queries in like the places that differ between these two oracles, then there's no way you could distinguish the two oracles. And turns out the same thing is more or less true even if our verifier is quantum, although we'll get a little bit of a loss. And this can be formalized via a very simple hybrid argument. This is dating all the way back to Bernstein et al. Okay, so the probability that a random query of our verifier, when we measure it to the no instance, the probability that it produces a point that differs between the yes and no instances is going to be around polynomial 1/t. Okay, so to recap, if we measure a random query of our verifier V given the proof pi to the empty set oracle, will produce a point that differs between the yes and no instances with some good probability. So what exactly are the two oracles that are showing up here? The first thing is that our empty oracle, by definition, is going to have the value 0 on all inputs. So that means that the unitary that it implements is going to be exactly the identity map. On the other hand, the points, the yes and no instances, will differ precisely on the points that are in our search relation R. So that means that if we run our verifier with basically no oracles and just like simulate the identity oracle, and we measure a random query, we're going to produce a point in R with good probability. And importantly, this simulation doesn't require any oracle queries whatsoever, because anyone can simulate this identity perfectly. So we have one tuple in our relation with that we generated without making any oracle queries. The question is, what do we do with that? The idea will be to try again, but with a modified oracle. We just got a measurement of a tuple xv. Let's stick that into the empty set and try to rerun the algorithm. So if our guess was correct, if our measurement ended up producing a tuple that was in the relation R, then the new oracle is still a no instance. And we still have the ability to simulate no oracle because we know the value of xv because we just measured it. So by the same logic, if we run the same exact algorithm as before, we will produce a point that differs between this full set and this smaller set with good probability. And the points that differ between these two oracles are exactly points that are in the relation that are distinct from XV. And we can do this with probably one of our poly T once again. So if we do this over and over, eventually we can produce many distinct tuples, like L distinct tuples, in our relation with some probability that will scale with exponentially in L. And we can do this as long as our no instances remain no instances, which means we can do this for like an exponential number of tuples. Okay, the last thing that we're missing is that our proof, like our algorithm, our sampler algorithm required a correct proof pi, and that proof can depend on the oracles in question. So we want to get rid of this dependence. So the key observation, which is due to Zhandry and Bostanci et al., is that even though in general, if we have a quantum state, measuring it can damage or disturb the state, if we have a classical string instead, then these strings are always reusable and clonable. Since we're dealing with a 𝖊𝖬𝖬 algorithm, that means our proof pi is classical. That means what we can do is we can guess the value of the proof once, and if we're correct, we can reuse it over and over, and we can clone it, and so we don't have to worry about damaging the state. Okay, so what will happen is when we guess this proof size, we'll lose a factor of 2 to the negative pi, and that's going to be like an exponential to the negative poly. This will decrease our overall success probability by that factor, but overall it should be okay because it will be amortized over the many tuples we guess. Okay, so we have now, if we have so as a recap, if we have a 𝖊𝖬𝖬 verifier V that makes T queries, then we'll produce an algorithm A that doesn't make any oracle queries, but nonetheless produces many distinct tuples in our relation R with some okay probability. So now let's consider the question of instead of sampling the functions h1 through hn and constructing A by running it on the simulation, what if we first ran A and then sampled our random functions after the fact? Well, since our algorithm A doesn't make any oracle queries in real life, then that means that the two experiments should actually have the same outcome. And so the question here is, what is the probability that A manages to produce L distinct tuples in a relation without even knowing what H is? So the simple claim here is that it will be simply 1/2 to the S of L for some S of L. S of L here is going to be the minimum number of distinct symbols that can appear among L distinct code words. And why is that the case? Because we produce basically tuples x1 v1 through xl vl, and v1 through vl are all different code words, and x1 through xr are supposedly what their hash values are supposed to be. So if we look at v1 through vl and their hashes, we'll see since it's coordinate by coordinate, any symbol that appears in a code word that doesn't appear anywhere else, we will have to guess its hash value. And because their hash functions h1 through hn are independent, we can only guess this with probably 1/2. And so the number of distinct symbols will dictate the probability that we can guess such hash value. Okay, so if we take our L to be the size of pi, then we'll get a lower bound that is roughly 1 over poly in n to the L. On the other hand, if we could bound a lower bound S of L to be roughly linear in L, then we would get an upper bound that is going to be roughly 2 to the minus n to the L, which is going to be much smaller than our lower bound. And that means we're going to get a contradiction because our 𝖊𝖬𝖬 verifier produces an algorithm that succeeds in producing L tuples in R with good probability, much better than should physically be possible. And so then we can conclude that our verifier V is in fact not a 𝖊𝖬𝖬 verifier. Okay, so our goal here now is to.
So just something that I wasn't sure I followed the connection. So initially the problem was just like a decision problem in which you're just trying to distinguish between two settings, which were about the size of S. And what was the connection between that and outputting those L tuples? Were you saying that?
Yeah. So the idea is if we give the the membership oracle for the set, either it's too easy or too hard, depending how big the sets are. And so if we start with the easy regime, we don't want to give access, like full access to this set membership oracle. So we're going to try to hide or gate access to this membership oracle. And the way we'll do that is that to figure out if X is in the set S, will require you to also produce like an associated witness Y that like such that X comma Y satisfies some search relation. And it'll be the case, it should be the case that Y is difficult to find for most X's. A valid Y is difficult to find for most X's. And so the kind of problem that we're taking here is going to be this code intersection search problem. And then the connection to that is essentially formalizes this intuition that any verifier that wants to tell if the set is big or large, the only way you can do that is basically to find, like, figure out for many X's whether or not it's in the set or not. And the only way you can do that is to produce a Y that such that X comma Y is in the relation. And so morally speaking, if we have a verifier, excuse me, a verifier that should give us some way of producing a lot of different tuples.
I see. So
that answers the question.
How should I think about this L? So does this L, for instance, refer to kind of like the number of queries to this oracle, or I guess I also missed exactly what L.
Yeah. Okay. So if I go back, I guess like actually this L, you can run this L for as long as you can run this algorithm for as long as you want, assuming L is not too big. Basically, like this algorithm will keep working until like what you're simulating is no longer a no instance. And so depending on like the way that we set it up, the no instances are anything where the sets are like size of at most like 2 to the n over 3 or something. That means that like you can run this algorithm for L all the way up to 2 to the n over 3. And the like goal of what for L, like what we want to set L to be is like we want to basically balance out this factor that we lose from guessing the proof. So when we guess the proof, we lose like an exponential factor, like 2 to the minus poly or n. We're going to want our L to basically be on the same order as the length of the proof. That way, like each time we guess, we kind of amortize this loss so that we only lose like a constant factor instead of this like really large upfront exponential factor.
I see. Okay, thank you.
Yeah. Okay. So I guess like So our goal here now is to get an upper bound on our success probability. We want codes that have this like property that they have very large S of L, which if we recall, S of L is basically like guiding like bounding how many distinct symbols must appear in L distinct code words. In other words, we want it to be so that whenever we have fewer than S of L symbols, then we can't use them to form more than L distinct code words. And it turns out this is exactly the notion of zero error list recoverability. And so unfortunately, the bad news for us is that the FRS codes that have been used in the past, they don't have good enough list recoverability for us. The good news is that there are actually some codes that have good enough list recoverability, and those are going to be these codes called multiplicity codes. And for these multiplicity codes, we know that for L that are even like up to exponential, we can still hope for S of L to be linear in L or so. And so this will mean that our proof can go through more or less. There's one caveat, which is that in order to use these multiplicity codes, we're going to have to make the rate of our code C and subsequently the distance C of the dual C-perp to be subconstant. And recall that that's going to be a bit of an issue because our error vectors that we had before that we're decoding from have Hamming weight roughly n over 2. And so we want to be able to decode from this high noise regime. So the idea, which has appeared in a couple other works in other contexts, is to kind of bias our oracles H1 through Hn. So for each each function hi, we're gonna basically let the value of sigma, instead of being equal to 0 or 1 with probably 1/2, it's now going to be equal to 0 with probably much closer to 1. And so that means, intuitively speaking, because our hash functions map most symbols to 0, it will be much easier to find a code word that hashes to the all 0 string. That means that if our X that we sampled was the all 0 string, then the associated error distribution will now be concentrated on vectors that have much smaller Hamming weight. And they'll be small enough that we can now decode our dual code C-perp, even though it has subconstant distance. Of course, this is a problem because what if we want to invert or find a code word that hashes to the all one string? Now that our hash functions h1 through hn are much less likely to hash to 1, that means that associated noise will be much larger than even before, and we already couldn't handle what we had before. Okay, so the fix is pretty simple. We notice that since we can only invert these low Hamming weight vectors, we'll simply try to enforce this condition. What that means is that anytime that we want to invert x, or we want to like find a code word that hashes to x, we'll instead find a code word that hashes to x followed by a lot of zeros. And our new oracle will also enforce this new condition that the x is appended by a bunch of zeros. So now that our Hamming, all the like x's that we're trying to find code words for have very low Hamming weight, we can use these biased oracles and get a 𝗊𝖬𝖬 algorithm nonetheless. And it turns out that if you balance the parameters correctly, our 𝗊𝖬𝖬 lower bound still goes through. So that's basically it for the 𝗊𝖬𝖬 and 𝗊𝖬𝖬 proof. The rest of the proof is just like balancing the parameters and making sure you get the details right, and then it's a fairly simple diagonalization argument. Okay, so
but
talk
so just to make sure, so like the new p that you are now choosing as the probability of outputting 0, that's still like a constant, right? Because I guess you cannot just make it like arbitrarily close to 1, because that would also affect the hardness, right? So you are choosing p to be greater than 1 over 2, but still constant, no?
Okay, so p will actually have to be a little bit. It will actually be pretty close to 1. So I guess like the distance of our code is not even constant. Our code is gonna have like, I guess what will happen is that the p will be like 1 minus 1 over like n to the 4th or something. And then the like what will happen is that you'll take like this. You'll add a lot of zeros, right? So the length of the code will be like n to the 5th or so. And
Yeah.
that means that if you like look back at the original thing, like we still get an exponential bound here. Like this 1/2 to the omega n of L, NL, like instead of 1/2, it'll be 1 minus 1 over n to the 4th, but the top will still have like n to the 5th instead. So we'll still be able to contradict, we'll still get like a working 𝗊𝖬𝖬 bound. And turns out that will be good enough. Like if we set those noise parameters, that will be good enough for the 𝗊𝖬 algorithm to still work.
I see. So you still have like hardness even by choosing it so close to 1. I see.
Yep. Okay. All right. So a little bit about the advice setting. So why doesn't, I guess, the Bostanci et al. Work, which gives you a 𝗊𝖬𝖬 algorithm separation, immediately also give rise to an advice style separation? So the key point here is that there are a few differences between proofs and advice. So the first thing is that proofs are in general untrusted, while the advice that you're given is always trusted. But on the other hand, like a proof can depend on the instance in question, while the advice is restricted to depend only on the input length. So these are fundamentally kind of two semantic differences. And as a simple example, we know that the halting problem, the unitary halting problem, is in like p-poly, and it cannot be in any like of these like uniform classes. So if we take a little bit look at the problem that Bostanci et al. Use, I'm not going to go into too much detail as to what this problem is, but it's this question of spectral correlation. So if people are familiar a little bit with this work, the idea is like you have two sets S and U which either are like unrelated to each other or they have some kind of correlation. And the way that they're correlated is kind of like if you do this like correlation operation, which is you like sandwich a Hadamard in between these two set membership queries, then either they'll be like they'll have a lot of overlap or they'll have less overlap. So that's the problem that Bostanci et al. Use, and they use that to separate 𝗊𝖬 from 𝗊𝖬𝖬. If you see here, this problem doesn't have much structure, and there's basically, it seems like only like one bit of information being encoded by this problem, namely whether or not the sets S and U are correlated or not. And so it seems kind of difficult to turn this into an advice problem if we only have this like one bit of information. For example, like how do we like, okay, so as we just said, like if we have like a unary language, like each input length, there is only one instance, then it's very easy to come up with a BQP poly algorithm because our single bit of advice can just literally say whether or not an instance is in the language or not. So we're going to need many different instances for the same input length. And the question is now it's hard to see like exactly how we set up this spectral correlation problem to have many instances for the same length. In particular, this like spectral correlation problem is in some sense like encoding some kind of quantum search problem that is hard, which is to find this set like superposition state over S, which will have good correlation. And because it has a quantum search problem underneath, like it'll be hard to kind of dequantize this and give like a classical oracle that can kind of like help you. Okay, so in general, the proof and advice separations are often like related to each other, but they don't imply each other. So it requires a little bit of work. So as we were saying before, like our set size estimation problem that we just covered for the QMA QCMA separation is also easy if you have advice, because we can simply give the bit that indicates whether or not we have a yes or no instance. That means that to lift the separation to the advice setting, we need a binary language. So for us, that's going to be easy because we already have a hard search problem. What we'll do is we'll sample a random language, like a random binary language, and our new oracle will be as follows. Whenever you solve essentially the search relation and the like X is in the set S, the oracle will simply tell you if X is in the language or not. And if we use the same algorithm, the YZ algorithm that we discussed before, it's not too hard to show that you can still put this language in BQP poly, QPoly if we take the advice state, same advice state as before. On the other hand, the intuition for why this is not in BQP poly is that the search problem, this classical search problem remains hard. And so even if we give access to this oracle O, if we can't solve the search problem, it's essentially going to be useless for the verifier. For the algorithm, the best it can do for most X's will basically be to guess. And that means that it will not be able to decide the language with high probability. Okay, so that's like a high level of how the advice separation works. The summary and takeaway from, I guess, this work is that in general, quantum states are very powerful, and their power seems to make them not reusable. In particular, our QCMA lower bound went through this reduction that like very crucially leverages the fact that classical strings are clonable. Also that sometimes small changes in perspective can make a very big difference in the proof. So our proof takes a different approach from earlier works before Bostanci et al. And it relies on slightly different codes than earlier separations based on this Yamakawa Zhandry algorithm, but it still has some similarities to the previous works. So it's really this like new perspective of this like verifier to sampler or guesser reduction that allows us to get a hardness result. And in particular, if you use the same ideas as before, or these FRS codes, and you plug that into this argument, well, you'll see is that you don't end up getting any meaningful upper bound. Okay. And also there's some side benefits of using a biased oracles. So previously, if you wanted to run the Yamakawa-Zhandry oracle, the algorithm, because our noise is going to be on the order of like n/2 our error vectors, that means that we actually, in order to decode our code words, we actually need to run list decoding. It turns out if we bias our oracles, like say to be like 2/3 biased or 3/4 biased, this allows us to move to the setting where we can use only unique decoders. That means we can improve the efficiency of this algorithm. And this is something that is even independent of our QMA or QSUMA separation. Like even if you just wanted to run this YZ algorithm by itself, using a biased oracle would make it faster. And it would still maintain most of the hardness. So some like future work or open problems that our work leaves. So one thing is you could ask is whether we can make this separation even conceptually simpler. I think that most of the proof is fairly simple. There's one thing that seems like it should work is that instead of using this like explicit multiplicity code, it would be nice if we could show that a random linear code would also work for the separation, but we currently don't have strong enough list recovery bounds to make it work. Other questions are like whether or not we can dequantize a lot of these unitary oracle separations that we do know, whether or not that's like a search decision no-go for QMA or this separation between QCMA and clonable QMA, as well as these very interesting like cryptographic separations starting with the work of Kretschmer. These are all unitary oracle separations, and it would be pretty nice if we could use ideas from here or from Bostanci et al. To get a dequantized version. Okay. And then lastly, are there any applications potentially to cryptography? So our result also separates the clonable versions of QMA and BQP QPoly from the unclonable versions. So there seems like there's a little bit of a connection to these ideas of quantum money and fire. And in fact, a lot of the ideas that show up there are also kind of present here and in the Bostanci et al. Work. So can we use some of these ideas from these separations for new constructions of various cryptographic objects? So that's basically all for this work. I guess if anyone has any questions.